Hello everyone, welcome back to my YouTube channel. In this week's video, I'm going to explain to you how you should answer numerical question for chapter 3. So altogether we have 4 different questions and let's start with the first one. Question number 1. Consider the following reaction between hydrogen gas and fluorine gas to produce hydrogen fluoride. The following reaction has an equilibrium constant of 620 at a certain temperature. Calculate the concentration of hydrogen fluoride at equilibrium if 4.5 mole of each component were added to 3.0 liter flask. In this question, you were given that the number of mole of each component is 4.5 mole and it was added to 3.0 liter flask. Therefore, from here, you can calculate the molarity. So, molarity is equivalent to the number of mole over liter. So the number of mole is 4.5 and the volume is 3 liter. So you get your molarity for each species is 1.5 molar. Alright, so next up what we are going to do is we are going to make the ice diagram. So you are going to copy back the reaction. So you are going to do the ice diagram. Initial molarity is the one that we have calculated just now for each component is equivalent to 1.5. So remember, the statement here is each component. So it means that it is inclusive with the product as well. So 1.5 for each. Right? So at change, here we'll need to do minus x, and this one plus 2x. So therefore, you will get 1.5 minus x, 1.5 minus x, and 1.5 plus 2x. Right? So from there, you will get your Kc. So what is your Kc? Whatever in the product. Because here you have 2, so to the power of 2 divided by whatever in the reactant, which is 1.5 minus x to the power of 2. And in the question, it's given that the equilibrium constant is equivalent to 620. So 620 is equivalent to 1.5 plus 2x square divided by 1.5 minus x square. So the easiest way for you to solve this issue is you just have to make the square root of both sides. So square root of this one and the other side. Therefore, you will get the square root of 620 is equivalent to, you're going to slash out the to the power of 2, so it's equivalent to 1.5 plus 2x divided by 1.5 minus x. Right, so we are going to do the normal quadratic, bring everything here, so it's equivalent to 1.5 minus x times the square root of 620 should be equivalent to 1.5 plus 2x. So now we are going to do the square root of 620. I'm going to copy the rest of the thing. So this one will be 24.899 is equivalent to 1.5 plus 2x. So you're just going to do the quadratic of this. You will get 3.5849 times 10 to the power of 1 minus 2.6899 times 10 to the power of 1 x is equivalent to 0. So you will get your x is actually equivalent to 3.5849 times 10 to the power of 1 divided by 2.6899 times 10 to the power of 1. Hence, your x is actually equivalent to 1.3327. So this is your x. But the question asks you, what is the concentration of HF at equilibrium? So we need to look back at our ice diagram. And at equilibrium, the concentration of HF is equivalent to 1.5 plus 2x. So by knowing the value of x, which is this one, so we are going to just plug in this value to get the concentration of hydrogen fluoride at equilibrium. So 1.5 plus 2x, whereby your x is equivalent to 1.3327. So you will get 1.5 plus 26654. Hence, you will get the final answer should be 4.1654 molar. So this is the final answer for the first question. Question number 2. Consider the following reaction. The Kc for this reaction is 42.5. If 0.05 mole of NO2, 0.122 mole of O2, and 0.30 mole of NO3 are mixed in a 1 liter container at 923 degrees Celsius, in which direction shall the reaction proceed? Alright, so in this question, you were given the number of mole for each component, and then the volume is 1 liter. So anywho, if you want to calculate the molarity, means that number of mole divided by liter, since it is 1 liter, so the molarity is actually the same as the number of mole. Right, so given to you is the value for Kc. So because all this number of mole is the initial number of mole, therefore what you can calculate is actually the Qc. So what I'm going to do now is I'm going to write the equation again. Right? So now in the ice diagram, you only have to fill in the initial. So the initial concentration is 0.05, and then 0.122, and lastly is 0.30, right? So what you're going to do now is you're going to find what is the QC. So whatever in the product, 0.30 to the power of 2 divided by 0.05 to the power of 2 times 0.122. So you just have to calculate this, and you shall get your QC should be equivalent to 2.9508 times 10 to the power of 2. Alright, so basically your QC is equivalent to 295.08, and then your Kc is equivalent to 42.50. In saying that, your QC is actually way bigger than your Kc. So since your QC is bigger than your Kc, the reaction shall proceed to the left. Means that you have produced too much product, so the reaction will reverse back, because your QC is actually bigger than your Kc. So this is the final answer for the second question. Right, let's move on to the third question. Determine the entropy of mixing when 3 mole of hydrogen gas and 3 mole of oxygen gas are mixed together in a container. So what we are going to do now is we are trying to find what is delta S mix, which is equivalent to negative NR, the summation of mole fraction, ln mole fraction. Right. So the first thing that you need to know is the mole fraction. So the mole fraction of hydrogen and also the mole fraction of oxygen. Right. So your hydrogen is 3 mole of hydrogen. So the number of mole divided by the total number of mole. So means that 0.5. So because these are the same, the number of mole of oxygen is 3. So 3 plus 3. So it's the same is 0.5. So how are you going to get the delta X mix is by using this formula. Then what value of R that you're going to use, right? So because you want it to be in joule per Kelvin, therefore your value of R should be equivalent to 8.314 joule per Kelvin per mole. Alright, so what is the value of your N? So we have 3 mole plus 3 moles means that it's 6. And then the value of R is 8.314 and the unit should be in joule per Kelvin per mole. Right? So the summation of mole fraction, ln mole fraction. So we are going to do the first one first, which is 0.5 ln 0.5 plus 0.5 ln 0.5. So one is for oxygen and the other one is for hydrogen. So in saying that, you will get the value is equivalent to negative 6 mole, because this is the number of mole. Then you need to times 8.314 joule per Kelvin per mole. And then this one is equivalent to negative 6.9314 times 10 to the power of negative 1. So basically what you can do is you need to slash out this one and then leaving you with joule Kelvin, because your mole fraction have no unit. Therefore you just have to press your calculator and you should get the entropy of mixing should be equivalent to 3.4577 times 10 to the power of 1 joule per Kelvin. So this is the final answer for the third question. Let's move on to question number 4. The acid dissociation constant of a weak acid has a value of 2.56 times 10 to the power of negative 4. Determine the concentration of H plus at equilibrium if the initial concentration of HA is equivalent to 4.25 times 10 to the power of negative 3 molar. Right, so this is a rather straightforward question. First of all, you need to do the equation for the dissociation process. So the acid is HA, so it shall dissociate into H plus and also A minus, right? So it states here that the initial concentration is this. So we are going to do the ice diagram. So the initial concentration is 4.25 times 10 to the power of negative 3. So initially there will be no dissociation, so 0 and 0. So whatever in the reactant should be minus. So this one minus x plus x plus x. So you just have to do the summation of this. At equilibrium is going to be 4.25 times 10 to the power of negative 3 minus x, and the rest are x's. Right. So from there, you were given the value of Ka is equivalent to 2.56 times 10 to the power of negative 4. Therefore, you can say that your Ka is equivalent to concentration of H plus times concentration of A minus divided by the concentration of HA. So what we are going to do now is just plug in the values from your ice diagram here. So you should get x squared divided by 4.25 times 10 to the power of negative 3 minus x should be equivalent to 2.56 times 10 to the power of negative 4. Right, so what we are going to do now is we are using the approximation method. Okay, so in this method, what we are going to do is we are going to remove the x over here. Alright, so since we have already removed that x, so it's easier for us to calculate the value of x. So x squared is equivalent to 2.56 times 10 to the power of negative 4. So you need to times 4.25 times 10 to the power of negative 3. Right. So you will get your x squared is equivalent to 1.0880 times 10 to the power of negative 6. Therefore, your x is just a square root of this. So you will get the value of x is equivalent to 1.0431 times 10 to the power of negative 3. Right. So what is the next step that you need to do, because at the moment we are using the approximation method, so we need to test whether this value of x is approved or not. So we need to test it by using test is equivalent to the value of x divided by initial concentration times 100. Right? So your value of x is equivalent to 1.0431 times 10 to the power of negative 3 divided by the initial concentration, which is 4.25 times 10 to the power of negative 3 times 100. And from here, you will get the test value is 24.5435%. So this value is actually bigger than 5%. So the value of x is not approved. So therefore, you need to do the successive substitution. Right, so moving on to the successive substitution. So we are going to do the Ka is equivalent to x squared. This is from your ice diagram just now. And then 4.25 times 10 to the power of negative 3 minus x. So remember, initially this minus x, we have already removed it. So now we are going to substitute the value of x that we have calculated just now with this new value of x. So x squared divided by 4.25 times 10 to the power of negative 3 minus the value of x that we calculated just now, which is 1.0431 times 10 to the power of negative 3. So now you are going to get a new value of x, because here your Ka is still the same. So 2.56 times 10 to the power of negative 4 is equivalent to x squared divided by 3.2069 times 10 to the power of negative 3. So therefore, you will get your x is equivalent to the square root of 8.2097 times 10 to the power of negative 7. So you will get your x should be equivalent to 9.0607 times 10 to the power of negative 4. Okay, if we look back at our ice diagram, we have HA that will dissociate into H plus A negative, right? So at equilibrium, this one is actually positive X and positive X. So the concentration of H plus is actually the value of X. So this is the value of X, which is the concentration of H plus at equilibrium. So the final answer is the concentration of H plus at equilibrium should be equivalent to 9.0607 times 10 to the power of negative 4 molar. So this is the final answer for the fourth question. Alright guys, so we have come to the end of this week's video. I would like to thank you very much for watching this video from the beginning until the end. I hope this video will help you to understand more on how to answer the quiz question for chapter 3. So I'll see you again next week. Take care, be good. Goodbye.